Hi everyone, I'm Sohun with my partner Karthik, and for our AA203 project, we looked at lane keeping of an autonomous vehicle using an iLQR-initialized NPC approach. So most commonly today, Model Predictive Control, or MPC, is the most commonly used approach for commercial vehicle lane keeping systems. And so to expand upon this, our goal for this project was to observe lane keeping performance of an MPC controller if we initialize it with an iLQR-generated reference trajectory. We make use of the kinematic bicycle model for our system dynamics, where our state variables are the positional coordinates of the vehicle with respect to an inertial frame, the heading angle of the vehicle, and also the velocity of the vehicle. And our control inputs are the steering angle of the front wheel and the acceleration of the vehicle. And our dynamics here are nonlinear. And so for our objective functions, first for iLQR, we use a quadratic cost function where we penalize deviations from the road or from the vehicle in the center of the road at each time step, and also the control magnitude. And then we take our iLQR generated solution and we transfer it over to MPC, where we use a cost function that is made for tracking the center of the road, and also works to minimize the control magnitudes. And since our dynamics are nonlinear, we have to use a sequential convex programming approach at each time step. And this is where iLQR generated trajectory comes into play. For the first time step, since we have to linearize our dynamics around a reference trajectory, we use the iLQR reference trajectory for the first time step to linearize around. And we also set the very first control for the MPC as the first control generated from iLQR. And the trajectory that we're tracking is an S-shaped road, as you can see here, with a 100-meter curvature radius.
So we use the iLQR for trajectory generation, as previously mentioned. So iLQR tries to track the curvy road, as you can see, and the steering angle and also signifies how the control input varies to help the vehicle follow the road. Especially during the curvy portions of the trajectory, we can see the lateral control effort works to keep the vehicle in the center of the lane. And the iLQR controller compensates for the curvy road attributes by balancing between staying in the path and applying the lateral control effort via the steering angle. After carrying out nonlinear MPC, after carrying the trajectory generation, the nonlinear MPC will track the center of the road and simulate the vehicle states. We calculate the lateral tracking error between the vehicle and road center at each time step. In the plot, as you can see, there are some lateral tracking errors. This is because of the inaccuracies in our modeling and the problem formulation as we use the simple kinematic bicycle model. For conclusions, the iLQR-initialized MPC has a near perfect tracking by shape road, except for the beginning and end of the trajectories, but could be because of inaccuracy in our modeling. MPC can be used for quick online planning with a finite horizon and can be readily integrated constraints. For future work, we're planning to use model-based reinforcement learning techniques to learn and improve the vehicle dynamics model using the MPC formulation. Thank you.
Thank you.